Hi guys, so welcome to the post-contest discussion of the Leetcode Biweekly. So just confirm once that whether I'm audible and my screen is also visible or not. So how was the contest? I guess this biweekly was pretty easier comparatively. So many of you have done well, I hope. Okay, am I audible clearly? Just confirm once. Okay, so I guess we can begin. So, hi guys, this is Abhinav and welcome to the Leetcode Biweekly 166 discussion. So, we'll start with the first problem, which is majority frequency characters. Okay, so you are given a string S consisting of lowercase English letters. The frequency group for a value k is the set of characters that appear exactly k times in S. Okay, so all the characters that appear exactly k times is called the frequency group of value k. Now, the majority frequency group is the frequency group that contains the largest number of distinct characters. Okay, so among all the frequency groups, one of the group would be called a majority frequency group, which it would be the group which contains the largest number of distinct characters. Okay, so you need to return a string containing all characters in the majority frequency group in any order. Okay, so you basically need to print the majority frequency group, all the characters in that group. If two or more frequency groups tie for that largest size, pick the group whose frequency k is larger. So in case of tie, you have to pick the group where the frequency is more. Okay, first thing for picking majority would be the number of members, distinct characters present in the group. Okay, based on that, you would select the majority. If they are two equal, then tie would be broken by their frequency. Okay, so let's see for this string, what you can say. For a frequency group of 4, we would say all those characters having a frequency 4 would come under frequency group of 4. So here we can see only D. This character D has a frequency of 4 in this string. Okay, none of the other characters have a frequency 4. So this D would come under the frequency 4 group. Under frequency 3 group, we can see A has a frequency of 3 and B as well has a frequency of 3. So both A and B come under frequency 3 group. And we can see C has a frequency 2. So under frequency 2, C comes. And we can see E has a frequency of 1. So under frequency 1, E comes. Okay. So likewise, we have grouped these characters into frequency group of 4, frequency group of 3, 2, and 1. Now, among these frequency groups, which group has the largest size? Here, size of this group is 1, just one character, 1, 1. But for this group, the size is 2. Okay. So the largest sized group here is this one with a frequency of 3. So this group A comma B would be the majority group. So we would print we would print a string BA. Okay, BA in any order, BA or AB would be valid. Okay. If you look at another test case, ABCD, here all of them has a frequency of 1. So in frequency 1 group, all these 4 characters come, and that group will only be the majority group. So you need to print all ABCD in your output. For this test case, you can see that P has a frequency of 2, F has a frequency of 2. So in frequency 2, both P and F come. G has a frequency of 1 and I has a frequency of 1. So in frequency 1, G and I comes. Now, since both these groups have two characters, same size, so we would see which one has a greater frequency. So here this group has a greater frequency. So tie would be broken on the base of frequency, and we would say P comma F would be our answer. So FP is our answer. Okay. So this is what you need to basically print. The constraints for the length of string is just 100. So you can do anything of n square, n cube, everything would be fine. Okay. So let's look at the logic, how we are going to solve the problem. So basically we have to just implement this thing, that if we have a string containing characters, all lowercase characters, so from A to Z, only characters would be coming, and this, let's say this string is of size n. So in this string, first of all, in order to group all the characters, what we would do, we would first compute the frequency of every character. So what we can do, we can use a map or just a vector that we have just 26 characters. We can say that A is at index 0, B is at index 1, likewise Z is at index 25. Likewise, we can store in a vector that f of, if we have to find the frequency of A, we would store that f of 0, 0 denotes A, is equal to whatever is the frequency of A. So we would compute this frequency. First of all, we would compute this frequency vector that can be easily computed by iterating through the string. Whenever we get a, we would do frequency of 0 plus plus. Whenever we get a B, we would do frequency of 1 plus plus, and likewise. Okay. So this way, after doing that, we would have computed our frequency vector, which would denote the frequency of A, frequency of B, frequency of C. We would get the frequency of all the 26 letters. Okay. Now, among these, now we have to group these characters into groups having equal frequencies. Okay. So what we would do, any character can have at max what frequency? There, what would be the range of frequency that they would have? So the size of this, if the size of the string is n, if n is the size of the string, then we can say at max, if all of them are A, then frequency of A would become n, and minimum would be 0. So all these frequencies would be in the range from 0 to n that we know. So what we can do is, in order to group them, we would create a group. Okay, how many different groups can happen? We would let's denote group 0. Let's denote group 0 as group of, okay, 0 would not come because we need to only have frequencies greater than 0. So let's denote group 1 as group of all characters having frequency 1. Group 2 as group of all characters having frequency 2. So how can we compute the list of characters present in a group? Once we have computed this frequency array, what we can do is we can use another vector of vector group, let's say, such that in group of whatever, if we have if we are saying that frequency of A is 5, then we would update that in group 5, we would push back the character A. That we can do. So this way, we would iterate through this frequency vector, and every time whatever the frequency is in that particular group, we would push back the character. So that way we would update that our group 5. This way our group 5 would denote would have a list of all those characters that have a frequency of 5. Once we have computed these groups, so after doing this, we would have group 3 having the list of characters having frequency 3, group 2 having the list of characters having frequency 2. After that, we just need to compare, go to every group, whichever group has the maximum size, we take that group as our answer. Okay. And if two of the group have the same size, then whichever has maximum frequency, we would take that group as our answer. So we'll iterate through all the groups and maintain a variable mx to compute. If the current maximum is greater than the previous maximum, we'll update that as our new maximum. That way we can iterate one more time and compute the thing that is required. Okay. So basically this was just implementation thing. Okay. So I'll just show you the code, how we are implementing it. Okay. So first of all, I take the frequency vector of length 26. Okay. I iterate through every character in the string and I say f of ch minus a. So basically, if there's a character A, then ch minus a would become 0. For character B, ch minus a would become 1. For C, it would become 2. So A would be denoted by 0, Z would be denoted by 25. So this way, in our frequency vector with indices 0 to 25, we will update all the frequencies from A to Z. After that, I take the size of the string and I create another vector of size n plus 1. So basically it would have indexes from 0 to n. Now this vector would store the groups. Basically this is our group vector. So vec of I would store all the characters coming in group I, group having frequency I. Okay. So we'll iterate through this I will iterate through the frequency vector which has indices from 0 to less than 26, and we'll update vec of fi dot pushback I. This way, whatever is the frequency in that particular group, we will push back I. Okay, so whichever has a frequency of fi, in that will push back the index I. Okay, now basically our vec of x would denote would have the list of all the characters having frequency x. Okay, then we'll take a variable mx to get the maximum group size. It would store the current maximum group size, and j would denote the index. Basically, j equal to 0 denotes the denotes the group 0. J equal to 3 denotes the group 3. Okay, so which group is the majority group, that is taken by j. Okay, now if vec of I dot size is greater than mx, if the size is greater than mx, we'll update our max and update our j. This is the j. Okay, and I've used greater than equal to sign and iterating from I equal to 1 to n. So if there is a tie where my size is equal to mx, then whichever element would come later would be put as the jth index. That way, whichever is coming later has a higher frequency, because we are moving in the sorted order of frequency. This I is the frequency. So our tie is also broken here. Whichever has a greater frequency would come after. So that would update the previous one, because we are using greater than equal to sign. Okay, so in j we have the majority group, so we'll print all the elements from group j. So vec j denotes the group j. So in our answer, we'll store all the characters from group j. Now in the group, I was storing 0 for a, 1 for b, likewise. So in that, if I add the character a, then 0 would convert to a, 1 would convert to b, and likewise 25 would convert to z. That I'll add in my answer string and return my answer string. Okay, I hope the implementation is quite clear. If you analyze the time complexity, this loop is running like 26 times. Okay, this this loop is running n times, the size of the string times. This is running 26 times. This loop again is running n times. Okay, and this is again the size of a group would be at max n. So we can say this would also run at max n times. Okay, so we can say our time complexity for the code would be order of n. Okay, same way our space complexity would be, we are just using a string of size n, frequency vector of size 26, which is constant size, vec of size n. Okay, so overall order of n space. Okay, I hope this first problem is clear to you all. Okay, so if it is clear, we can move to the next problem. Okay, so let's move to the second problem, which is climbing stairs. So you are climbing a staircase with n plus 1 steps numbered from 0 to n. You are also given a one indexed integer array cost of length n, where cost I is the cost of step I. Okay, so you have a staircase with n plus 1 steps numbered from 0 to n, and you have a cost array which would tell cost I would have some cost for the step I. Now what the actual cost is, you can jump, if you are at step I, you can jump to step I plus 1, I plus 2, or I plus 3. Okay, so you can jump to any one of these 3 steps, and the cost of the jumping from step I to step j is defined as cost j plus j minus I square. Okay, so if you are jumping from I to j, whatever is the value of the array at index j, the cost j, that plus the difference in j and I square, this would be the total cost to jump from I to j. You start from step 0 with a initial cost of 0, return the minimum total cost to reach step n. Okay, so you have to basically return the total cost to reach the step n if you start with step 0, and these are the jumps you can make. Okay, so this is the problem. Let's look at one test case and understand. So here, if you look at this test case, we have this cost array, n is 4. Okay, so you start with the step 0, you want to reach step 4. Okay, so at step 0, your initial cost is 0. Now you can, from step 0, you can jump to either 1, 2, or 3. You can jump 3 steps forward, any one of the 3 steps ahead. Okay, so if you jump to step 1, the cost to jump to step 1 would be the cost I cost vector of this 1 plus the difference in the indices, which was so here we'll index this also. Let's say these are the indices. Okay, this is the array and these are the indices. Okay, so if we jump from 0 to 1, the difference between the indices is 1 minus 0 square plus this cost 1. So this cost would be 1 plus 1, 2. Okay, and if we jump from 0 to 2, then our cost would be, this difference would be 2 minus 0 square plus this cost 2. So it would be 2 square plus 2, which would give us 6. And same way, if we want to jump from here to 3, this difference would be 3 minus 0 square, which would be 9 plus this cost 3. It would be 12. So these are the 3 different jumps you can make initially. So you have to just determine what would be the most optimal jump in order to reach step 4. So here one way to jump would be, you start with 0, then let's say you reach 1 with a cost of 2. Okay. Now once you have reached 1 with a cost of 2, from 1 you can jump to 2, 3 or 4. Let's say again you take one step and jump to 2 with a cost of 2 plus 1 square, which would give us 3. So with a cost of 3, let's say you jump to 2. Okay. Next, what you can do is, with a cost of 3 plus 1, 4, you can jump here, or maybe with a cost of 2 square, 4 plus 4, 8, you can jump here. Okay. So let's say we jump here next from 2 to 3. This would have a cost of 1 square plus 3, 4. From 3 to 4, it would have a cost of 4 plus 1 square, 5. And we reach 4. So this way we reach 4 with a cost of 2, 3, 4 and 5. That makes us a total cost of 14. So let me check if 14 is my, no, 13 is the most optimal. So the most optimal way was jump from 0 to 1, 1 to 2 and then 2 to 4. Okay. So if instead of jumping from 2 to 3, if we directly jump from 2 to 4, then we can say that our cost would be jump from 2 to 4, 4 plus 2 square, 4. So this would have a 4 plus 4, 8 cost. Then our total cost would become 2 plus 3 plus 8, which would make a cost of 13. So this was most optimal, jumping from 0 to 1, 1 to 2 and 2 to 4. Okay. So now how do you calculate this optimally? The constraints given is 10 to the power 5. Okay. So looking at this problem, maybe if you have solved enough DP problems, you would remember that this is like a very standard DP problems. So what you can do is just take a DP state where DPI denotes that what is the cost to reach step I, what is the minimum cost to reach step I. Okay, so if we take this as our DP state, then can we write the transitions for it? Okay, so let's look. Let's say we want to reach this step I. Okay, so what are the number of ways through which we can reach step I? We know from any step we can jump either to I plus 1, I plus 2 or I plus 3. So like in the reverse, what we can say is, if we want to reach step I, we can come here either from I minus 1 by jumping one step, or from I minus 2 by jumping 2 steps, or from I minus 3 by jumping 3 steps. These are the only 3 possibilities for the last jump that we made. Okay, so we would just try to minimize among all the 3 possibilities. So we would say that DPI is either if you came from step I minus 1. So if I'm telling that you came from step I minus 1, what would be the cost? The cost to reach I minus 1, first of all, that would be denoted by DPI minus 1. DPI minus 1 denotes the cost to reach I minus 1. Once you have reached I minus 1, you took a jump from I minus 1 to 1. What would be its cost? Its cost would be the cost of I plus their difference square. So this would be the cost array of I plus the difference square is I minus 1 square. So I minus 1 is 1 square, which is 1. So plus 1 we can say. So either this is one way to reach here, or we can say that if we came here from I minus 2, then we would say that DPI minus 2 would be the cost to reach I minus 2, and then we take a jump. So we would say DPI minus 2 is the cost to reach I minus 2, and then the jump would have a cost I plus I minus 2 square, which would be 2 square. 2 square is 4, so plus 4. Okay, and the third option available to us is, if we are reaching here from I minus 3, then from I minus 3 we can say that dp I minus 3 would be the, in a similar way we can write that dp I minus 3 would be the cost to reach I minus 3, plus the cost to jump from I minus 3 to I would be cos I plus 3 square, you can realize, so plus 9. So we can say that these are the three possibilities to reach I. So whichever gives us the minimum cost, we would take that and say that is the most optimal minimum cost to reach step I. So we can say that minimum among all these three is our DPI. So this we can say is the transition for our DP. Okay. So this was our state. This was our transition. Let's just write the base case and we are good to go to code our solution. So what would be the base case for the DP? So you can see DPI is being computed using DPI minus 1, I minus 2 and I minus 3. So we can say what base should we choose so that we can compute all the DP. So to know I minus 1, you should have known I, to know I, you should have known I minus 1, I minus 2 and I minus 3 previous vectors. So basically you need to move from 0 to n. If you are moving, then when you are at I, you would know the previous values. So you have to move from 0 to n, and what base case you should take? So you should take DP0, which would denote the, let's say we are taking one based indexing. Let's say we are taking one based indexing, then dp0 would denote an empty step, the step 0. Okay, so dp0 denotes the step 0, and we know it's given in the problem also that the cost to reach step 0 is 0. So dp0 is basically 0. This would be one base case, and then we are using previous three states, so we would write three base cases so that all the transitions can be written smoothly. So we'll also write dp1 and dp2. If we write both of these, then from dp3 we can start computing using our transitions. Okay, so what would be our dp1? Our dp1 would be the minimum number of steps to minimum cost to reach step 1. The only way to reach step 1 is we are starting with step 0, jump one step and reach step 1. So this would be cost of step 1. Okay, now in the cost array it was 0 based, so the first element in the array would be cost 0, because the cost array was given 0 based. That's why I'm writing cost 0, but it should be I. Okay, here I'm writing cost I, then dpi is to reach step I. So this I'm considering as one based index, that's why I'm writing cost I, but in the code it was given my 0 base, so I'll write minus 1 in all these three. Okay, so in the code I'll write cost I minus 1 to denote the cost of the ith step. Okay, in 0 base. So that's why dp1 would be cost 0 plus 0 minus 1 square, which would be 1. Same way for dp2, we can say it would be either we reach this second step, from the 0th step we took a jump of 2 and we reach here, or from the first step we took a jump of 1 and we reached it. So we can say it would be the minimum among, either you start with 0 with a 0 cost and you reach 2, so cost 2 would be the cost to reach 2 plus the jump from 0 to 2, we would have a cost of 4. Okay, either this, you jump from 0 to 2, or you jump from 1 to 2. So cost 2 plus dp of 1 would be the cost to reach 1, and then when you jump from 1 to 2, then cost 2 plus 1 square, that would be the total cost. So we can say dp2 is the mean of this. Once we have written these base cases, these are our base cases. Okay, we know the base case, transition and state of our dp, we can easily write the code. Okay, I hope this logic is clear. We can, let's move to the code. The code would be the same thing that I have written here. Okay, so one edge case you have to consider is if n is equal to 1. If n is equal to 1, then we cannot write dp2, we don't need to reach step 2. So like that we can, you can handle separately. If there is only one step, the only cost would be cost 0 plus 1. Okay, this dp1 would be the only cost. We don't need to compute further. Okay. Otherwise, if n is greater than equal to 2, we can compute using our dp. So we write the base cases. dp0 is 0, dp1 is cos 0 plus 1, dp2 is min of cos 2 plus 4, min of cos 0 plus 4. Okay, in cost vector it is given, I think, 1 based only. Okay, it's 0 based. So yeah, so dp2 would be cost 1 because I am using 0 based indexing here, so it would be cost 1. Okay, so cost 1 plus 4, either this or cost 1 plus dp1 plus 1. So dp1 plus cost 1 plus 1. So these base cases are done. After that, we'll write the transition from I equal to 3 to n. Our transition would be dpi is the min of I minus 1 plus cost I plus 1. So this cost I is coming in all the three. So we can take it out of the min function. So I've written this cost I minus 1 out of the min function, and in the min function I've written these things. Okay, so it would mean the same. In the min function I've written dp I minus 1 plus 1, dp I minus 1 plus 1, I minus 2 plus 4, I minus 2 plus 4, and I minus 3 plus 9. Okay, min of all these is my dpi. I write the transition, and my answer, final answer, would be dpn, the minimum cost to reach step n. Okay, so this way, this is the code for the problem. I hope this second problem is also clear to you. Is there any doubts? Maybe you would have not used memoization with the recursion, that's why it's showing TLE. Please check your code. If you use memoized recursive DP, that should pass. Any other doubt? If you're doing the memoization correctly, it doesn't matter you write iteratively or recursively. For N1E5, it would pass. There would be some mistake. That's why it is showing TLE. If you can send the code, then I can tell. Okay. So, okay. I guess we can move to the next problem. Can't find your message. How do you analyze constraints? Basically, by looking at the constraints, you get to know what time complexities would be acceptable for the code. So looking at 1E5, you know that you can run a code of O of n or n log n at max. You cannot run n square. That's what time complexity analysis is. Okay. I hope that's okay. Let's move to the C problem. Okay. So you are given a string S consisting of characters U, D, L, and R, representing moves on an infinite 2D Cartesian grid. Okay, so U means you move from xy to xy plus 1. Basically, you move up. D means you move down to y minus 1. L means you move left to x minus 1 comma y. So x would decrease by 1. R means you move right. So x would increase by 1. Okay, now you are also given a positive integer k. You must choose and remove exactly one contiguous substring of length k from S. Then start from coordinate 0, 0 and perform the remaining moves in order. Okay. So basically, you should choose exactly one contiguous substring of length exactly k from the string S, and then you just remove one contiguous substring of length k from S, and after removing that substring, whatever remaining string you get, using that string you perform the operation. So start with coordinate 0, 0 and perform all the moves in order from the remaining string, and after performing the moves you would reach some final coordinate. Now return an integer denoting the number of distinct final coordinates reachable. So depending on the different contiguous substrings that you would remove, you may get a different final string which you would use, and you may reach a different final coordinate. Now you need to find how many distinct final coordinates you can reach. Okay, there may be that through two substring removals you may reach the same final destination, maybe taking a different path. They would count as same. You need to just count how many distinct final positions you would reach. Okay, so let's say for example, if you are given this string LUL and k is equal to 1. That means you have to remove a substring of size 1. So either you can remove this L, you would get UL. If you remove this U, you would get LL. If you remove this L, you get LU. Now, with all these three different strings, you may reach different final positions. So if you use UL, from 0, you move up and then you move left. So you reach -1, 1. Okay. If you use LL, you move left, left. So you reach -2, 0. If you use LU, then you go left and you move up. So you reach -1, 1. So here you can see that this -1, 1 and this -1, 1 are the same. So they are not distinct. So only distinct points are -1, 1 and -2, 0. So there are two different distinct final positions that you can reach. So your answer is 2. Okay. So I hope you would have got what the problem is asking you to do. Okay. So here if you see this string, your k is given as 4. So with 4, the only substring available is removing the whole string. So if you remove the whole string, you get an empty string. You don't perform any operation. So your final destination would be the coordinate 0, 0 only. So there is only one distinct point, which is 0, 0. 1 would be your answer. Okay. So I hope you would have understood the problem. Now again, the constraints are given as 10 to the power 5. That means we need to do something in order of n only. We cannot go n squared. So now how do you solve this particular problem? Okay. So you are given a string having u. This string only contains character u, d, l and r. Okay. So u denotes that you move up, d denotes you move down, l left, r right. Okay. So whenever you perform any one of the moves, what would happen? Either your x would increase by 1, or your x would decrease by 1, or your y would increase by 1, or your y would decrease by 1. Okay. So currently if you are at any position x, y, after performing certain number of moves, what you can say that whatever the combination of moves you perform, whenever you perform u, your y goes +1. Whenever you perform d, your y goes -1. So if let's say you perform n times u and let's say m times d, then what would be your final y coordinate after performing n times u and m times d? You would say n times you do +1, m times you do -1. So total plus n minus m. This would be the change you would make to the y coordinate. So if you start with y equal to 0 and you do these number of operations, you would reach y is equal to n minus m. Okay. So now if you do, let's say, n minus 1 times u and m minus 1 times d, then also you would say that you would do plus n minus 1 minus m minus 1. That is same as n minus m. Okay. So in this method also you would reach a y is equal to n minus m only. Okay. So there may be different ways through which you reach the same destination point. So, but on what factor does the net final destination point depends? That depends on the frequencies of u, d, l and r. So we can say that your net final x comma y is, if you start with 0, 0, the frequency of the number of times y coordinate was the number of times you got u minus number of times d, frequency of u minus frequency of d. And your same way we can say the x coordinate was whenever you move right, you do x plus 1, left you do x minus 1. So we can say the frequency of right minus frequency of left is your x coordinate. So your final x comma y coordinate is basically frequency of r minus frequency of l comma frequency of u minus frequency of d. Now you need to check how many different such points, unique points exist. So if you can compute all the final destination points, okay, so how many final destination points would exist? How many different substrings can you remove of size k? First of all, if you think like that, then you have a string of size s, a string of size n, and you want to remove a substring of size k. So either you can remove the first k characters, okay, or you can remove from the second character to the k plus 1th character, or from the third character to the k plus 2th character. Likewise, like a window, you can move a window of size k. So if you start with a window of this size k, you can move one by one. You can move this window till the end. Okay. So how many different such windows would exist? You start with 0. Let's say you start with the index 0 up till k minus 1. This would be your first window, and your last window would be ending at n minus 1. N minus 1 is the last coordinate, and this coordinate would be n minus k. So if you start with n minus k, you would reach till n minus 1. So from 0 to n minus k, you would say that you have n minus k plus 1 different windows that you can pick. Okay, so these are the total number of different strings that you would get for each of the windows that you remove. Now for all these n minus k plus 1 different strings, if you can compute their final destinations, then you can just store that final destination in the form of a pair x comma y. Okay, and you want to find number of distinct, so you can store all of them in a set and compute the size of the set. That would be the number of distinct characters, distinct final destinations. So you can store all the final x comma y pairs in a set and compute the size of the set. Finally, that would be the number of distinct points. Now, how do you optimally compute that for every segment that you remove? What is your final destination? Okay, so if you think that, let's say you remove this segment. Now, since you have n minus k plus 1 different segments, then for every segment, if you apply the operations n minus k times, then your time complexity would be order of the number of different sets is n minus k plus 1. And for every set, the size of the string would be n minus k. So if you perform all the operations, then this overall time complexity would be something like order of n square. If k is very small, it would go something like order of n square, or k is big, it would go something like k square. So this n square won't be accepted, because n is given up till 1e5. So you need to somehow find some optimal way to do this. So what you can do is, let's suppose, so now the next observation here is, if you compute, like what you need is how many different final destinations exist. Now, if this removal was not there, then whatever string that you have, if you do all the operations, then the whatever is the sum of frequencies of u, d, l, and r, it would depend on that only. So for the complete string, that sum would be some exact final destination that you would reach. And if you remove a substring from that, you can effectively say that if you remove this much part, okay, then the order of operations actually doesn't matter. You first perform a u, then perform a l, or first a l, then a u, that doesn't matter. So basically you can say that you are removing all these operations from that final destination. You can perform a reverse, that when you remove a u, when you are adding a u, you do y plus 1. So when you remove a u, you can say you do y minus 1. So if you simulate, then for every substring that you remove, for the remaining string, the different final destinations that you would have is same as if you compute the final destination for this particular string. So because you only need to compute different final destination, not the exact final destination. So the different final destinations would be, final destination considering the whole string would be some constant minus the final destination using this substring. So how many different constant minus some thing exist is same as how many different these things exist. So instead of computing for the remaining substring, we can compute for the current substring only. So we can compute for any window of size k, if we perform the operations only in this window, what final destination we reach, put all of them in a set, whatever number of distinct points you get, that would be your answer. How do you optimally compute for every window? Let's say you compute for this first window, you compute your final x comma y, then remove this point, add this point, you get the next window. Remove this point, add this point, you get the next window. So you can use a sliding window approach. Remove this ith point, add the I plus kth point. So you can update your next final destination using the next window. So in this way, in O of 1, you can, once in O of k, you can calculate for the first window, and then you in O of 1 you can update every window for all the n minus k plus 1 window. So in total, k plus 1 into n minus k plus 1 time complexity, which is equal to n, in order of n time, you can compute this using a sliding window approach. Okay, I hope this thing is clear to you. Let's look at the code. Okay, is there any doubts in the approach? Okay, so let's look at the code. So what I'm doing is I've taken a set of pair in which I'll store all the final destinations to get the number of distinct final destinations. Now I start with x equal to 0 and y equal to 0. Now I would compute my xy for the first window of size k. So for the first window of size k, I iterate from 0 to less than k. If si is 0, I do y plus plus. If it is if si is u, I do y plus plus. For d, I do minus minus. For l, I do x minus minus. For r, I do x plus plus. So in this way, I update my x comma y for the first window. Whatever final xy I get for the first window, I put it inserted in the set. And then I'll slide through all the windows, remove the ith character, add the I plus kth character, remove the ith character, add the I plus kth character. This way I'll strike through the window starting from I equal to 0 to s dot size minus k. So the last window would start from n minus k. So this would be the starting point of the last window. So if I iterate through n minus k till n minus k minus 1, then when I remove it and add the last one, I'll get the last window. Okay, so this is the last, as n minus k minus 1 is the last removal that I have to do in my sliding window. So I run a loop like this. Then if si is u, so for the ith character, I remove that from the window. So removing I means for u, removing u means I do y minus minus. Here for u, I was doing y plus plus, but since I have to remove, I'll do the opposite. For u minus minus, d plus plus, l would be plus plus, r would be minus minus. I do all the opposite thing to remove the si character. Okay, and for si plus k, I'll add it. So I'll add si plus k. So for u, I do plus plus, as I did here. For u plus plus, d minus minus, and same way for all. Okay, so I remove the ith character, added the kth character, I get the final destination for the next window. I insert it into the set. Okay, and then after inserting all the final destinations for all the set, for all the final destinations into the set, I return the size of the set as the number of distinct final destinations that I would have. Okay, so I hope the code is clear. Time complexity for this part would be order of k. Insertion in the set takes log n time, and then this is running n minus k times. I do insertion in the set which is taking log n time. Okay, so this overall would run n log n times. Okay, or n minus k log n times. Okay, n minus k times log n. So this I can say is my final time complexity, is order of n into log. Okay, so this would be well accepted for n25. For space complexity, we can say that I'm using a set which would have a maximum size of n if there are like n different final destinations. So order of n, we can say, is the space complexity. Okay, so I hope this problem is clear to you. Can we move on to the next problem? Explain with an example. Okay, I'll explain with an example if you are not certain about it. Let's take one random example. Let's say you have a string something like LU DU LDU, something like that. Okay, so and let's say k is equal to 4. So you have to take windows of size 4, this window, this window, this window, and this window, all these windows of size 4. So what I'm telling that if you remove this window and compute for this Then number of final points for removing this and then computing is same as computing for this. So we'll compute for this one. So I start with x equal to 0, y equal to 0. For the first window, I compute for L means left means x minus minus, up means y plus plus, D means y minus minus, U means y plus plus. So in the first window, I get x equal to -1, y equal to 1. Okay, this I'll put in my set. So in my set, I'll put -1, comma 1. Okay, now I have to update my answer for the next window. Okay, so let's update it for the next window. So I have for this window, in order to move to this window, I have to remove this L and add this L. So removing L means L was left, so removing L means going right. So x plus plus, x becomes 0. And then adding this L means going left, x minus minus, x becomes -1. So this window got updated to this. And my new final destination is -1, comma 1, which is already present in the set. So inserting it would not insert it again. Okay, now let's update. I have to remove this U and add this D. So removing U means moving down. So y minus minus 0. And adding D means moving down, y minus minus -1. So I have updated my window to this, and my new x comma y is -1, comma -1. This we would insert into the set. Okay, again I remove this D, so go up, do y plus plus, add this U, so again go up, do y plus plus. So after updating this, what we get is -1, comma 1, which is already present in the set. So the number of distinct values in the set is just 2. So our answer for this case is 2. Okay, if you even compute for all the cases, then you would get, if you remove this, the string that you get would be LDU. Then if you remove the next window, string you get is LDU. If you remove this window, string you get is LUU. If you remove this window, you get LUD. So if you compute for all these 3 different strings, LDU is left, down, up. So this would be -1, comma 0. LDU is again -1, comma 0. LUU is left, up, up. So -1, comma 2. LUD is left, up, down. So again -1, comma 0. So number of distinct points you get is -1, comma 0 and -1, comma 2. So there are only 2 different distinct points. Now you would notice these and these were different because here I was computing for the removed part. But as I explained, computing for the removed part, the number of different subsets, different distinct values in the set is the same as removing for calculating for the complete minus removed. Okay, so I hope using this dry run it is clear now. Okay, so yeah, I guess we can move to the last problem now. So the last problem is maximize alternating sum using swaps. So you are given an integer array nums. You want to maximize the alternating sum of nums, which is defined as the value obtained by adding elements at even indices and subtracting elements at odd indices. Okay, so basically alternating sum is whenever you get an even index you add it, whenever you get an odd index you subtract it. So num0 minus nums1 plus num0 minus nums3 and so on. This is the alternating sum of the nums array. Now you want to maximize this. Okay, so how do you maximize this? You can do some swap operations. What swap operations are allowed? You are given a 2D array swaps where swap I is pi comma qi. So you would have some pairs, a list of pairs where every pair denotes that you can perform a swap between the index pi and index qi. So pi and qi would be 2 indices. So basically that means that in between these 2 indices you can perform a swap. These swaps can be performed any number of times in any order. So you can perform any number of swaps between these 2 indices. Okay, in any order you can choose between any 2 different swaps that you do. Return the maximum possible alternating sum of num. So after doing these swaps in the array, what is the maximum possible value of the alternating sum. So let's look at it from an example. So this is like a simple example where you have 1, 2, 3. Allowed swaps are from 0 to 2. This is index 0, this is index 2. So you can use a swap between this index 0 and index 2, 1 and 2. So you can do a swap between index 1 and index 2. So these are the allowed swaps, you can say. Okay, so this and this are the allowed swaps available to you. So how do you maximize it? What you are doing here is swap num0 and nums2. So you swap these two, it becomes 3 1. So nums is now 3 to 1. Okay, next you swap 1 and 2. So you swap these two, nums becomes 3 1 2. Okay, next you what you do is swap 0 and 2. You swap these two, it becomes 2 1 3. Okay, so after it becomes 2 1 3, now if you look at the alternating sum, the alternating sum is plus 2 minus 1 plus 3, which is 5 minus 1 4. The alternating sum becomes 4, and 4 was the maximum you can reach whatever type of swaps you do. Let's look at another example. Here 1 2 3, and only swap available was between 1 and 2. So you can swap these 2 and 3 positions, or you may not perform any swap. Here without performing swap, your sum was plus 1 minus 2 plus 3, which is 2. And if you perform this swap, you get an array 1 3 2. Then your sum would be plus 1 minus 3 plus 2, which would give you 0. So this becomes lower only. So better would be not perform any swap, and your sum remains 2. So that is the maximum you can get. Here no swaps are available, so you cannot do anything. Array would remain as it is. The sum of the array would be plus 1 minus this plus this minus this plus this minus this. So 3 times minus 1e8, I think 1e9 it is. So minus 3e9 plus 3. So it's minus 2 9 and 9 7. Okay, so this is the problem. The constraints are n is again till 1e5. The values of nums can go up till 1e9. The number of swaps is also till 1e5. And okay, so basically you are given n numbers, size of the array is 1e5, and number of swaps available is also 1e5. So you cannot do something like order of n into m or something, or n square or like that. You have to do in order of n or order of m. M is number of swaps I'm referring to. Okay, so now let's try to look at it, what we are doing. How do we solve this problem? So if you look at this array, okay, so how do you like maximize the alternating sum? So you have plus minus plus minus plus minus plus minus like that. Okay, so in order to maximize the alternating sum, what you would want, you would do, the values of the array remain the same. With swaps you can just shuffle those values. So your final sum is plus for these indices and minus for these indices. So if there is a value x here, it would contribute plus x, but if the same x moves here, it would contribute minus x. So what would you want in order to maximize it? Let's say you are able to perform any swaps. Okay, you can just swap any two numbers, you can shuffle the array anyhow. Then how would you maximize the final alternating sum? You would try that in these plus positions you have higher values, and in minus positions you have lower values. This way you would add more and subtract less. Then only you can maximize the overall answer. So first greedy intuition, this you should get, that you should try to bring higher values in the plus positions and lower values in the minus positions. Okay, now but here you are limited to the swaps, that you cannot perform a swap to any index so that you just shuffle them up. If it was allowed that you can perform swap in any of the index, then your answer would be among all the values that are present in the array. What you can do is you can sort the array in decreasing order, place the first half greater values in the plus positions and the lower half of the smaller values in the minus positions. This way only you can just maximize your final alternating sum if all of the swaps were allowed. But now when you are limited with swaps, then what you can do if you try to think? So how is this swaps given to you? Available swaps. You are given like this. Let's say these are the indexes in zero based index. Okay, so let's say your swap array is given as, let's say you are given 0, 5 as one pair, 0, 5. You can do swaps between 0, 5. Let's say you are given 2, 3. You can do swaps between 2, 3. Let's say you are given 3, 5. You can do swaps in 3, 5. Let's say you are given some 4, 6. You can do swaps in this, and something like 6, 8. You can do swaps in this. Let's say this is your swap list of swaps that you can do. Okay, now these you can say that you can swap these positions, swap these positions, swap these positions, swap these positions, swap these positions. If you look at the positions that you can swap, if you look here 0 and 5, you can swap the members here, and this 5 is again connected to 3. So let's say you want to swap something at 3 with something at 0. What you can do is you can swap it with 5, bring it at position 5, and then you can do a swap between 5 and 0, so that whatever was there at 3, it went to 5 and then it went to 0. So effectively you were able to swap 0 and 3 by using these two swaps. So basically you can say these 0 and 3 was not directly connected by a swap, but indirectly you can always perform a swap between them. Same way 0 and 5 are not directly connected, but you can perform a swap using this swap 2 and 3, swap 3 and 5. Okay, this way you can like indirectly perform a swap between 2 and 5. So what you can say that whichever are like directly or indirectly connected, among all those you can just perform any type of swap and shuffle any element anywhere. So here you can say that 0, 5, 3 and 2, these were in a single connected component. You can say that if you denote these swap operations, if you put an edge between these two, okay, then if you consider these indices as nodes and consider these swap operations as edges in the node, then you can say that all those nodes which are connected directly or indirectly. Okay, so when you are doing giving a undirected edge in a node, then whenever two nodes are connected, they come under the same component. So for all these nodes which are in the same component, among them you can just independently apply swap operations in the same component to shuffle the values anywhere that you desire. So here 0, 2, 3, 5 were in the same component, and same way 4, 6, 8, they were in the same component. So among 4, 6 and 8, if you want to swap 4 and 8, you can swap 4, 6, 6, 8, and then this way you can bring 4 to 8, and then 6, 4 with that swap, 4 and 6 would get swapped. So 4, 6 and 6, 8 already you can perform. So basically you can just shuffle it anyhow that you desire. So what you can say that you can consider these list of indices from 0 to n minus 1 as n nodes in a graph, and these edges as these swap operations pairs as edges in the graph. Then you can say that for every independent component that you get it in the graph, for every component of the graph, you can perform a independent swap operation. Okay, so now what you can say that for every component that you get in the graph, you can shuffle it anyhow. So what is the best way to do it? Like I had explained earlier, that if it was allowed that you can swap anything in the array, then what you would do, you would sort the values and use the greater values with plus sign, smaller values with minus sign. So for any component you can do the same thing. In this component, how many plus signs are there? This is a plus sign, this is a plus sign, this 4 is a plus sign, this 5 is a minus sign. So in this component you can say that in this component you have 3 plus signs and 1 minus signs. Okay, so whatever values are there in this component, sort those values in decreasing order, and for the top 3 values give them plus sign, For the bottom value, give it a minus sign and add them up. That would give the maximum value from that component. Do it for every component. This way you would maximize the overall value. Is this logic kind of fine? So if you look at this test case also, so if you look at this test case, you have nums as 1, 2, 3. So index 0, 1, 2, you have value 1, 2, and 3. So consider these three indexes as nodes in the graph, and the edges you have is from 0 to 2. So 0 to 2, there is an edge, and 1 to 2, there is an edge. So if you consider this graph, what all components are there in the graph? So you can see all these three nodes are connected. So this is a single component graph. So you can just shuffle these values in any order. So this would have a plus sign, this index would have a plus sign, this would have a plus sign, this would have a minus sign. So we have 2 plus signs and 1 minus sign. So sort this, you get 3, 2, 1. For the first two values, assign them plus, last value assign them minus. So you get plus 3 plus 2 minus 1, you get 4. This was the answer for this test case. Same way for this, you are not given this particular swap. This is not given to you. Basically, this edge is not given to you. So if this edge is not given to you, then you would say that this is one component and this is another component. So for this component, you would individually maximize. So for this component, you have 1 plus sign and 1 minus sign. So sort the values. Sorted values would be 3, 2, give a plus here, minus here. So plus 3 minus 2 is 1. So 1 is the maximum for this component, and for this component there is only one value that would receive a plus sign, so it adds a plus 1. So overall we get plus 1 plus 1, overall plus 2 as the answer for this test case. Okay, so I hope this logic is clear to you what we are doing. Now how do we implement this graph logic optimally? One way is, from this graph it would have n nodes and m number of edges. Both n and m are till 1e5, that is fine. Then in this graph you can perform a DFS. Through the DFS you can just group these nodes into components. Okay, so through DFS you can find the components in a graph. If you know the algorithm, just apply a for loop from 0 to n minus 1, apply a for loop for every node which is not visited, the number, and apply a DFS from any unvisited node. The number of times you apply visited is the number of components, and in every DFS, all the nodes that you visit in the DFS would come under that component. That is one way. Another way to group components is using DSU. Okay, so the code I have written is using DSU because I already had the template of DSU with me, so I copy pasted it and it was faster to write that. But if you don't have the DSU template, you can use it using DFS. That was more simpler. Implementation wise, if you take time in writing DSU, but it depends on you. Whichever feels faster for you, you can apply that method. So the code I'm going to show would be for the DSU code. Okay, using DSU, what you can do is, whenever you have some nodes, just iterate through every edge. Whenever you add an edge, you can insert it. You can union these two through the DSU. So whenever you union two nodes through the DSU, so you add every edge, union. Then in every component, for every component, if you check their parent, then every component would have a single top parent. So by checking the parent of every node, you get the for all the nodes belonging to same component, they would have a single parent. So that way you can group them into components. You can find the groups for every component. The parent would be the head of the component. So this way I've implemented. I'll show it through the code only. Okay, so what I'm doing is, this is the template for DSU. You have this DSU class where if you want to create a DSU of size n, you use to parent and rank. So I'm using the rank for DSU. So parent dot assign n plus 1 0. So assigning all the parents and rank. So all the rank would be 1 and all the parent I would be I itself. Okay. So this way I form a DSU with n different groups whose parent is itself. So all the n are in different components. There are n different components. So there are n plus 1 different components actually here, but we only need requires from 0 to n minus 1 according to the indexing. Then the find set function, which is if parent x is x, return x, otherwise find set parent of x and assign it to parent of x. Using this optimization, we reduce the time complexity of DSU to almost order of 1 instead of log n. And then union set function, if you find the parent, or if you want to union between these two nodes, find the parent of first node and second node. If they are equal, they are already in the same set, no need to do a union. If they are unequal, whichever has a higher rank, assign the person with lower rank to the assign the person with higher rank to the lower rank. This way, assign P2 to P1, lower rank to higher rank, and increase the rank of the person with one. So this way, you do the union. Okay, I hope you know about DSU. So this was a template for DSU. Then what we are doing in the code is take the size of nums, create a DSU of size n. Okay, and then for every swap operation that I have, that contributes to a edge in the graph. So basically, for every swap, if I can swap v0 and v1 for every pair, do the union of that pair. So if I get 1 comma 2, I do union of 1 and 2. Okay, so I do DSU dot union set, I apply that operation. After that, I have done the union of using all the swaps. So I have grouped this graph into components. Okay, now how do I find all the values present in a particular component? So I create a vector of vector vec n. So vec I denotes that whoever has a head of the component equal to I would store the list of all those values in vec I. So initially vec I is empty. Okay, it has an empty vector inside. Now for every index from 0 to n minus 1, if DSU dot find set I, whichever is the head parent of I, in that particular vector, I'll push vec I. Okay, so this way vec I would have all the group of nodes coming in the same component. Then I'll iterate through every group present in my vector. Okay, so V would be every group, this inside vector that I push back in every group. So if this V is empty, that some particular doesn't have any group, I just continue. If V is non-empty, I'll calculate. So for any non-empty group in V, I have the list of indices in that group. So what I'll do is I'll have a vector of values, and for every index in the group, in values, I'll push back nums I. So I'll have the list of values at those indices. Okay, so if I have these, let's say in a group, I get the indices 0, 2, 3, and 4. Okay, these are in a single group. So when I get to index 0, I put the value present at index 0. When I get to group 2, I put the value present at 2 and 4. Likewise. So all these values are pushed into the vector val. Okay, so in val, I'll have the list of values in the particular group, and I also need to get the count of positives and negatives. Okay, so in C, I'm getting the count of negatives. Okay, so at odd index, I have a negative. So whenever index is odd, I do C++. Okay, so C gives me the count of negatives in the group. Okay, now I sort this values vector, and if I've sorted them in increasing order, then in increasing order, I'll place the smallest C values would be assigned negative sign, rest values would be assigned positive sign. Okay, so if I have one negative sign, then among these 4 values, the smallest one value would get negative sign, rest of the 3 values would get positive sign. Okay, so C is the count of negatives. So I move to this values vector in sorted order. If I is less than C, so if I'm below C in the index, so for the first C values, I do answer minus equal to val I. For the rest values, I do plus equal to val of I. Okay, so this way I update my answer to maximize my overall sum. And once I have iterated through all the components, I return my answer. Okay, so I hope this code is also clear to you. Yeah, you can obviously do it simply with DFS, but as I told, I had the code copied, so it was fast for me to write during the contest. That's why I did like this. Both of the things are fine. Both of the ways are fine. If you want, I'll put the code for DFS also in the link. I'll write the code for DFS and put it. You just need to run a for loop from I equal to 0 to n, and if not visited I, you can just run a DFS starting with index I, okay, and just use some global value k, and whenever you are running a DFS, do k plus plus. So that means whenever you run a DFS, you are at component number k, push back all the nodes that you visited that time in the DFS in the kth component vector. Next DFS, you would put in k plus 1th, k plus 2th. This way, you will compute this vec that I was computing, that list of indices present in every group. This would be computed like this. If you run a DFS, and inside the DFS, you can do a vec of k dot push back the ith index for which you are running the DFS. Okay, this way you can do it using DFS as well. Okay, so I hope this logic is fine to you. Okay, what if there is a certain constraint on swap, like each swap can will be used only once? That would contribute to a different problem. That would require some different thinking, I guess. And whether it is solvable or not, that would be also a question. So okay, for this problem, this was the solution, but would become an entirely different problem altogether. So yeah, this is the code for the last question. It would be shared in the description of the video also. If you want to check it out, you can check. Okay, so if a swap is not present to the index, that means that index in itself is in a single component. So if I'm computing the DSU, if no swaps are present, then from index 0, index 1, index 2, let's say n is 2, n is 3. So these would be 3 and no indices are present. So everyone would correspond to itself as its parent in the DSU. So there would be 3 different components with a single node. So single node component would mean it would just add to its AND depending on its sign. Okay, so that would be done in this code only. When I'm iterating through, if there is the size of v is even 1, then I'll iterate through v, push back the value in my val vector, sort it. Sorting one value doesn't take any effect, and whatever, if c was negative, c is 1, it would add plus. If c was negative, it would add minus, otherwise plus. Okay, accordingly, for even size 1, this would compute it. Okay, I hope it is clear. Is there any other doubts, or should we end the session? Okay, so thank you so much, guys, for tuning in. Goodbye.